Hi, I'm C-C Chen. In this video abstract, we discuss our paper revealing the degree of magnetic frustration by non-magnetic impurities. This work is in collaboration with Moritz, P Devereaux from SLAC National Accelerator Laboratory, Applegate and Rajiv Singh from University of California at Davis. So here we attempt to address the question, how do we use the response to non-magnetic impurities to distinguish models that vary in the level of magnetic frustration. Although the newly discovered ionic-type superconductors provide context for this study, our results apply more broadly to other frustrated spin systems as well. Geometric frustration is a central theme in condensed matter physics. It arises when magnetic interactions on a lattice is incompatible with the underlying crystal geometry. The simplest example of geometrical frustration is antiferromagnetically coupled spins on a triangular lattice, where not all spins can be simultaneously antiparallel. Magnetic frustration also occurs in other systems. For example, spin systems on a square lattice can be frustrated when the nearest neighbor and next nearest neighbor interaction are both antiferromagnetic. The role of frustration has now been discussed in the newly discovered ionic-type superconductors. In these materials, ion spins are ordered in a stripe pattern, with the moments smaller than 1 Bohr magneton. And this phenomena could be accounted by a frustrated J1, J2 model. When J2 is larger than half J1, a collinear antiferromagnetic ground state is stabilized, and the moment is suppressed due to the system's proximity to a magnetic quantum critical point. On the other hand, collinear antiferromagnetism could also result from a J1A, J1B, J2 model, where one has antiferromagnetic interaction in one direction and a ferromagnetic interaction in the other. In this case, the system remains unfrustrated. To distinguish these models, the important question is how magnetic frustration can be quantified. Here we explore the possibility of probing frustration by the response of host materials to non-magnetic impurities, such as zinc substitution or ion vacancy. In particular, we investigate how local magnetic moments near impurities are affected. We find that in the frustrated J1, J2 model, a non-magnetic impurity induces strong quantum fluctuation and results in substantially reduced magnetic moments. In contrast, the anisotropic J1A, J1B, J2 model shows enhanced local moments near the impurity site. The local field distribution could be probed by nuclear magnetic resonance. The nuclear hyperfine Hamiltonian consists of Zeeman interaction, nuclear dipole-dipole interaction, and the interaction between nuclear and electron spins. For nuclear spin larger than 1/2, there's also interaction from the nuclear electric quadrupole moment. In ionic types, at low temperatures, the ion atoms are magnetically ordered, which would further split the resonance signals into a 6-peak structure. Because of hyperfine coupling between arsenic nucleus and iron spins, non-magnetic impurity could affect the local field distribution and therefore change the NMR signals. We calculate corresponding arsenic 75 NMR signals at 1% impurity doping for the two models under study. The anisotropic J1A, J1B, J2 model shows a clear 6-peak structure in the resonance signal. On the other hand, for the frustrated J1, J2 model, these peaks are substantially broadened and show an asymmetric pattern. The difference in the change of magnetization could distinguish between models that vary in the degrees of magnetic frustration.